So what do we do in the case of a design specification where we cannot create a functional gauge associated with the geometric tolerance? That's when we have to consider using what we call soft gauging. And soft gauging is going to involve some measurement equipment that we'll talk about later, as well as some computational methods to determine whether or not we are within specifications. So similar to what we saw with functional gauges, we're also concerned about the potential sources of error. They will be different because we're using a different approach. And how can those errors occur when we use the soft gauging? And we'll see that it gets a little more complicated because we're no longer dealing with a physical representation of a part. And then what are the impacts of those errors on the results? First of all, what is soft gauging? Essentially what we're going to do is take measurements on the surface. Again, the surface is corresponding to the features of interest. So when we think about the geometric tolerance, we're going to have to look at surfaces associated with the datums, as well as surfaces associated with the feature we are trying to check. Once we take these measurements, then what we'll do is make inferences about the part geometries. In order to do this, we'll need some type of instrumentation to gather the data. And once we have our data, and typically what we're talking about here is some set of x, y, and z coordinates, we'll create a geometric model based upon the measurements, and we'll perform some type of statistical analysis and then some optimization to check whether or not we are within specification. As you can see here, there's a lot more involved in the actual inspection process than what we had with the functional gauges. So the simplicity of the functional gauge is certainly an advantage. The downside, of course, is in some cases we're not able to use it. And what we'll find out here is we get a lot more information based upon the measurements that we're making and the analysis that we perform. So there is an advantage here. The big advantage is I'll know what the actual deviation is of those part geometries, whereas the functional gauge was not checking for the actual, it was only checking at a limit. In the case of the geometric tolerance, we were just looking at the virtual condition. Here we're going to know exactly how that specific surface deviates. It's also widely applicable to many different feature specifications. So we can do just about any feature that is designed on a part. And then we've got the flexibility from part to part. We don't have to have a bunch of functional gauges sitting on a shelf, but we're able to switch between parts rapidly based upon our measurement system. It does have its disadvantages, though. In order to get the system up and running and everyone trained, we're going to have a higher initial cost than those functional gauges. So we're going to make an investment, and that could be anywhere from, let's say, $150,000 up to $1 million. Then we're going to have to do something similar to what we saw in CNC, machine instructions. We're going to have to program the device to perform the inspection. That way we get consistent inspection, and that helps reduce the variability of the results. A major concern here, and we'll be pointing this out as we go along, is the techniques that are employed in the soft gauging are not consistent. And as a result, we could have disagreement between, say, a supplier and their customer as to the outcome of a specific part feature. Because we're using a measurement system, depending upon the technology we're using, the time it takes to measure the surfaces can be excessive. And therefore, it reduces perhaps the number of inspections that you can perform and or part features that you can check. Of course, it's going to require a higher level of training and someone who is committed just to that inspection process versus the functional gauge. We could train many different operators to use a functional gauge. Let's start with probably the most common type of measurement system, and that is a coordinate measurement machine. With a coordinate measuring machine, which I believe you used in 248, what you're doing is capturing points on a surface. And that's done with a physical probe or a laser, and we're making contact with the surface. So here in this figure, what you see is our workpiece and the surface that we happen to be measuring, and here's our probe that is connected to the rest of the CMM. Well, what we're actually recording here is not the point on the surface, because the way this technology works, when we make contact, we have a very sensitive switch in the probe head, and that indicates to the control system that we should record the location, the actual location, and that is similar to what we saw with CNC. It's the center of this probe, which is a sphere. If we know the offset, then we know essentially this surface here based upon offsetting the surface recorded here. So if we move this probe up and down parallel to the surface, we can define a plane out here, and then we can offset that plane to the right and tell you where that surface is located. Now, of course, there are sources of error associated with this technology. One obvious source of error is, even though we'd like to think that the probe is a perfect sphere, it is going to have imperfections. It's not completely uniform. So if you think back to roundness of a sphere, there will be some finite deviations around that sphere as we go from point to point. And so when you initially used the coordinate measuring machine, what you did was qualified that probe by touching off on a standard sphere, and then it reported back to you what the radius of the probe was, and it also gave you the standard deviation for the probe. And that gives us an idea of the contribution of the probe to the errors that we're going to find when we actually measure surfaces. Now, that's one source of error. Another potential source of error is temperature. So these devices need to be maintained in a controlled environment. And the reason for that is just basic physics. You know that as temperature fluctuates, if we put this out on a shop floor somewhere, which is not temperature controlled, what will happen is all the guideways on the coordinate measuring machine, as well as metal components within the coordinate measuring machine, will expand and contract based upon the temperature. And so this can lead to significant error in your results. And for that reason, we put it in a temperature controlled environment. We also need to isolate it from vibrations, because that will also contribute to our error. As you can see here, it's going to require a significant effort to ensure that we're going to get good results. And that effort is involved in isolating our measurement system from the rest of our manufacturing system. In order to use this, what we'll have to come up with is a fixture, and we've already covered that. Fixture in this case does not require a lot of clamping force, because we're not applying large forces. What you would like to prevent is any motion due to an operator perhaps bumping into the part and therefore having to start all over again. The key issue in terms of any of these measurement systems is the number of points that you are going to sample, because this will be proportional to time. And then where should these points be located if they're limited? And here we want to cover the surface of interest. So we want to get a reasonable sample of that surface so that we can determine its characteristics. And then finally, once we know the number of points and where they're located, then we go back to this notion of path planning. How do we visit those points to minimize our total inspection time? Because as you recall, inspection is non-value added. Once I have my set of points, we need to construct soft gauges. And the soft gauges are essentially geometric models. So when I say geometric models, I'm talking about a theoretical model that corresponds to something in our design spec. And as you can see here, these are all theoretical concepts: a line, plane, circle, and cylinder. We're going to take our set of points and somehow find those types of geometries, and we'll see how to do that a little bit later. Well, let's think about my points and how I might arrive at a geometric model. Here I've got 4 points that I've sampled, and I'm interested in determining a line from that set of points. And so if you think back to your statistics, you probably recall that you use something called least squares, linear regression, to determine a line based on a set of points. So we could take a similar approach here. I've got 4 points, and one approach is to find some type of optimal fit to the geometry, in this case indicated by the red line. So I might take my 4 points and say, well, they should be evenly distributed about that line, and that might give us an optimal fit. So in least squares, you probably remember talking about minimizing the sum of squared deviations. So if this represents a deviation from the line, and I measure that and then square the value, add it up, I'm looking for this line. So we're going to rotate the line, translate the line, until we get that minimum sum of squared deviations. So that would be one approach. Another approach, and this has to do with the consistency of the technology. So if you recall, one of the issues here with using this technique is that we can have inconsistency between different users of the measurement system. And this is where that can come into play. So if I look at the first approach, which was minimize the sum of squared deviations, I obtain the top line, versus if I use a different technique and say what I want to find is the boundary. In other words, all points on or above that line. And so here's my boundary indicated by that line. Obviously, I end up with a different geometry, and that can lead to different results in terms of the soft gauging. So we can think about what we mean by an optimal fit. The traditional approach is to use what we call the LP norm estimation for a set of points. In this case, we have n points that we've measured. And as we indicated before, what we're going to do is take the deviations, that's the d sub I, and the deviation is from some theoretical geometry. It could be a circle, a cylinder, a plane. And then we're going to supply a value for p, and it has to be greater than 0. And when we put that value in there, we're going to take the pth root of that sum. So here what we've got is the sum of our deviations. Now if p is equal to 2, you can see what's going to happen here. We're going to square our deviations. If p is equal to 1, I'm just going to take the absolute value of the deviations. And that would be my LP norm estimation. And then we can use that in some type of optimization to determine what is the best fit for our points. So let's think about distance here, because it's a commonly used metric. Here I've got 2 points in space, x, y coordinates, and the question is, what is the distance between those 2 points? So if we look at it from the point of view of the LP norm estimation, it would look like this, where we're going to subtract the difference in the x, the difference in the y coordinate, and if we had a z coordinate, but we're not going to worry about that for right now, we would also subtract that. Then we're going to raise it to the power p, and then take the pth root of that. So if I look at the distance between these two, we commonly think of the distance as being the straight line distance between those 2 points. Now that is only one distance, and that distance would correspond to a p-value equal to 2. But what if I set p is equal to 1? So if I put a 1 in here, then what I'm going to have is 2 minus 0 plus 1 minus 0, and that's equal to 3. Whereas for p is equal to 2, I had the square root of 2 squared plus 1 squared. These are definitely not the same. And again, this goes to consistency of techniques. What does 3 represent? It's certainly not the straight line distance here, but you can think of it as traveling 2 in this direction and then 1 in that direction, or what we call the rectilinear distance. Whereas this is the Euclidean distance. The shortest distance between 2 points, or is it? So let's put our p-values into that expression and see what our distances look like. We already did the expression for p is equal to 1 and 2, and we saw that 3 is a longer distance than 2.24, that was square root of 5. But now what happens if we keep increasing our p-value? You can see it rapidly converges on the number 2. So we've just shown that the shortest distance between 2 points is not the straight line between the 2 points. So let's go back and look at that. What we see here is that a value of 2 is essentially the x component in terms of a distance between those 2 points. So it represents just this distance, which is definitely shorter than the Euclidean distance. What does that really represent? What that represents is minimizing the maximum distance between those 2 points. These 3 different approaches will give us 3 different results for our soft gauge. Well, let's look at a whole feature, and we'll just look at in 2 dimensions here. We might use a p-value equal to 2 based upon what we just did, and take the sum of square deviations of our individual 4 points from this theoretical circle. And we'll try to minimize that. What do we mean? What we really mean is that we're going to change the location of the center of the circle, and we're going to change the radius. They're interrelated. So I can change the value of x and y for the center, and I can grow and shrink the size of the circle based upon changing the value of r. So we'll change these 3 parameters until we find the minimum value for the sum of squared deviations. Or conversely, what we could do is take a small circle, as you see here, and all the points are outside the circle. Then what we're going to do is keep expanding the circle until we find the largest circle, right, the max radius that fits inside the points. So we're essentially saying all the points have to lie either on the circle or outside the circle. So it is the inscribed circle of our set of 4 points. We want to find the largest one, subject, of course, to the fact that the distance, r sub I, is the distance from the point to the center of the circle, that those distances have to be greater than or equal to r, which is just saying that we are either on the circle or outside the circle. That would give us the largest hole from that perspective. Now, this result will be different than the result that we obtain using this technique, and that's why we say our results can be inconsistent. Well, if we reverse it to a shaft, we have a solid feature now. We can take the exact same approach, minimize the sum of squared deviations, and now we find that some of the points are inside the circle, some of the points are outside the circle. Now, physically, we know that in terms of the actual surface, this point, for instance, here, is on the feature. However, it is not on this perfect geometry that we fitted. And so it doesn't exactly represent what's going on with the surface. Again, we are trying to find the theoretical geometry. So instead of using that approach, we might take a similar approach to the hole and find the circumscribed circle around the points. So we want to find the minimum circle such that all the points fit inside the circle, or conversely, the circle is outside all the points. The criteria here is that each distance from the point to the center of the circle has to be less than or equal to the radius of the circle. So essentially what we'll do is contract this circle here and keep making it smaller, as well as moving it around, until we get the circumscribed circle such that all the points are either on or inside the circle. Again, what's the minimum circle that we can have? That would give us a cylinder representing that feature. So the results here will obviously be different than the results using the least squares approach. So the key concepts to remember here is, what is the geometric model that we are trying to use as a soft gauge? How do we collect the points associated with our surfaces? And what kind of technique are we going to use to determine this geometric model, because it will have major impact on your results. So the steps in creating this soft gauge involve measuring the surface of the part feature, and we can do that by collecting data using a measurement system such as a CMM. Then we're going to estimate the parameters of a geometric model using some LP norm estimate, and then we'll use the deviations from that geometric model as a way of determining a soft gauge.